Picture a panel of expert judges, each carrying their own biases, arguing over a single decision. You could just average their scores and call it fair. But wouldn't it be smarter to learn which judge to trust on which kind of case, and weight them accordingly? That's exactly the leap stacking makes. Instead of blending models with a flat average, it trains a whole new model whose only job is to learn how to combine the others. That's how a surprising number of competitions get won. Let's take it apart. So what makes stacking different from just pooling a bunch of models? Here's the contrast side by side. Plain averaging treats every model as equally worthy. It adds up their predictions and divides, no questions asked. That's simple and often decent, but it's also a little naive. A weak model drags the average down just as much as a strong one lifts it, and you never learn that some members deserve far more say than others. Stacking hands that decision to a model of its own. A small metamodel studies how each base model tends to perform and learns exactly whom to trust, and when. Instead of a blind average, you get a weighted blend that the data itself chose, which usually squeezes out more accuracy than equal votes ever could. Here's the part that trips people up. Stacking has two levels, and the order really matters. Watch the pipeline. Start at the base level, where you train several models that are deliberately different. Say a random forest, a gradient-boosted tree, and a logistic regression. Each attacks the problem in its own way and makes its own kinds of mistakes, and that variety is exactly what the next level is going to feed on. Now collect their predictions, but carefully. You generate them out of fold using cross-validation, so each base model only ever predicts on data it was not trained on. Skip this and you leak the answers, and the whole ensemble overfits spectacularly. This discipline is genuinely the crux of the entire method. Feed each model's cross-validated predictions into a metamodel as its input features. This second-level model, usually something simple like a linear regression, sees how every base model voted on each example and learns how much weight each one truly deserves. It's a model whose training data is other models' opinions. Out comes the final blended prediction straight from that metamodel. Because it learned whom to trust from the base model's real track records, this combination typically beats any single member and usually beats a plain average too. That learned blend is the whole payoff of stacking. Boil it all down, and 3 ideas carry stacking. The first idea is the metamodel itself. Rather than fixing the combination rule by hand, stacking learns it. A second-level model takes the base predictions as input and discovers the best way to fuse them, turning combination into something you train rather than guess. The second idea is what keeps it honest. The metamodel must be trained on out-of-fold predictions, generated by cross-validation, so it never sees a base model scoring data that model was trained on. Forget this and leakage creeps in, and the ensemble overfits without any warning. The third idea is where the gains come from. Stacking thrives on diversity. The more differently your base models fail, the more the metamodel has to work with. Keep the base learners varied and the metamodel simple, and you get an ensemble that regularly wins competitions. Alright, let's lock in what matters. Stacking trains a metamodel to learn the best way to combine several different base models into one prediction. The base models make predictions, and a simple metamodel takes those predictions as features and learns whom to trust and how much. The critical rule is training that metamodel on out-of-fold predictions from cross-validation, so no model ever grades data it already saw. It costs more compute and complexity, but when the base learners are diverse, it beats plain averaging and wins Kaggle leaderboards. If machine learning explained without the hand-waving is what you're after, come explore the full collection at Standarity.com. See you over there.